Hello everyone, so welcome to a new series about Calculus 1 with proofs. So this course is not going to go over what proofs are in general. I'm going to have a separate course about Introduction to Mathematical Proofs. This series is just going to be about Calculus 1 and proofs involving Calculus 1, and I'm going to assume you already have some knowledge about how mathematical proofs work. So let's jump into our first topic, which is limits. So say I have a function. Let's call this function f of x. And I want to find the limit of the function at a certain point. So when we're asking for this, what we're asking for is, as I take x values that are getting closer and closer to a, what are the corresponding f of x values getting closer and closer to? So the notation for this is we say lim f of x, x arrow towards a. And when we ask for this, what we're asking for is, as x approaches a, what is f of x approaching? So let's see an example. Let's take the function x plus 1, and let's find the limit of x plus 1 as x approaches 2. So this will be pretty simple. Let's draw a graph. And here is the graph of x plus 1. And the point 2 is going to be somewhere around here. So let's take x values that are getting closer and closer to 2. So if we take like 1.9, then the corresponding value of our function is going to be 2.9. Then if we take like 1.99, the corresponding value is going to be 2.99. And same with the other side. If we take f of 2.1, this is going to be 3.1, and then we take f of 2.01, this is going to be 3.01. So on both the left-hand side and the right-hand side, these numbers seem to be getting closer and closer to 3. So we say that this limit equals 3. Now you may think that was pretty obvious, since we just plugged in the number 2 into our equation for f of x, and we got that this was the answer to the limit. However, we're going to see that that's not always the case. So let's see an example where we can't simply plug the value into the function. Let's consider the limit of x squared minus 25 over x squared minus 4x minus 5, and let's take the limit as x approaches 5. So if we try to do what we did in the previous example, let's plug 5 into this equation, and we're going to immediately run into an issue, which is that when we plug 5 into the denominator, we get 25 minus 20 minus 5, which equals 0. So at 5, this function is undefined. But we know this function has a limit at 5, and the way we know that is by looking at its graph. The graph of this function looks something like this, where the number 5 is right here. So as we take x values that are getting closer and closer to 5, we see that these f of x values are getting closer and closer to some number. The issue is just at 5 exactly, the function is undefined. So one way we could solve this problem is we can try and create a new function that looks exactly the same as f of x, but it's also defined at the point 5. And this is going to be helpful because it's going to be a lot easier to compute the limit at 5 of this new function. since it will just be the value of the function at 5. And since our other function is going to be the exact same at all points other than 5, we know that the limit of our other function as x approaches 5 is going to be the same as the limit of this other function at the point 5, and that limit is just this new function evaluated at 5. So let's try and create this new equation. And the way we're going to do that is by manipulating this old equation and trying to simplify it. So what I notice is that both the numerator and the denominator of this function can be factored pretty easily. The top is going to factor like this, and then the bottom is going to factor into x plus 1 and x minus 5. And now we can see that this minus 5 and this minus 5 are going to cancel. However, we can only perform this cancellation for all values of x other than x equals 5. When x equals 5, this denominator is undefined, so this whole equation just doesn't really make sense. So we see that this equation is equal to this one for all x except x equals 5. And then notice that this is exactly what we wanted to do. We wanted to create a new equation for the function that was the exact same, but it doesn't have the issue where it's undefined at 5. What we now know is that the limit as x approaches 5 of our original function is the same as the limit as x approaches 5 of this new function. Because remember, when we're talking about the limit at a certain point, all we're asking is what are the values of the function approaching as we approach that point. We're not actually asking what is the value of the function at that specific point. And this limit is going to be really easy to compute, since we just have to plug the value of 5 into this equation. So we get that this limit is equal to 5 plus 5 or 5 plus 1, which is equal to 10 over 6. So this 10 over 6 is the limit as x approaches 5 of this function, which we know is the same as the limit of as x approaches 5 of our original function, since these two equations are the same for all values of x except for x equals 5, which we know does not matter when we're talking about the limit at 5. So let's see one more example that's going to be similar to this one, where we can't simply evaluate our original equation at this limit. But in this one, the algebraic manipulations are going to be a bit more complex. So let's take the limit as x approaches 3 of the function x plus 1 minus 2 over x squared minus 9. So the graph of this function looks something like this. Where the point 3 is right here. So we can see, just looking at this picture, that as we take x values getting closer and closer to 3, the corresponding f of x values are getting closer and closer to one specific number, this one right here. However, at 3 exactly, this function is undefined, because again we have the issue where there's a 0 in the denominator. So let's take the same approach as last time of trying to create a new equation for f of x that produces the exact same outputs and is defined at the point 3. And then we know that the limit of our original function is going to be the same as this new function evaluated at the point 3. So let's try to create that new equation by manipulating our old one. And the first thing I notice is that the denominator can be factored. However, simplifying the numerator is a bit more complicated. So there's a trick that you kind of need to memorize, which is that whenever you're working with square roots, oftentimes the best way to simplify them is to multiply and divide by what's called the conjugate. And what the conjugate is the same expression. So we're going to have square root of x plus 1, but instead of subtracting by 2, we're going to add by 2. And then in order to keep this true expression, we're going to have to divide by the same thing. So this is essentially the same as multiplying by 1, which we know is not going to change what the equation is equal to. But this is actually going to allow us to rewrite this equation in a new format that is defined at 3. So let's simplify the numerator. We've got square root of 1 plus x times square root of 1 plus x. So we're going to end up with 1 plus x. Then we got square root of 1 plus x times 2. And then we've got minus 2 times square root of x plus 1 and minus 2 times 2. And then now in our denominator, we're multiplying by the same thing. So we now have x minus 3 times x plus 3, and all of this is multiplied by square root of x plus 1 plus 2. So now we can go ahead and simplify this numerator. This is going to cancel with this, and then we have 1 minus 4. So in the numerator, we're going to end up with x minus 3 over x minus 3 times x plus 3 times square root of x plus 1 plus 2. And then now we'll see that this minus 3 and this minus 3 are going to cancel. However, we can only perform this cancellation for all values of x except for x equals 3. So this is how we're going to arrive at our new equation. So what we see is that this new equation is equal to our old equation for all values of x except x equals 3, which is precisely what we wanted, because when we're finding the limit of our old expression at 3, we don't actually care about what the value of the function is at 3. We just care about what it is near 3. So we see that the limit of our function as x approaches 3 is the same as the limit as x approaches 3 of this new function. Looking at the graph of this new function, we see that as x approaches 3, f of x is approaching f at 3. So to find this limit here, we just go ahead and evaluate the function at the point 3. And all of this simplifies to 1 over 24, which is the answer to our original limit. So those were some examples of limits that exist. Now let's see some limits that don't exist. So let's try and take the limit as x approaches 0 of the function 1 over x. So if we look at the graph of this function, it's going to look something like this, where this is the point 0 right here. So we see that as we get closer and closer to 0, the value of the function keeps getting bigger and bigger and bigger, and it keeps going towards infinity. So we see that as x approaches 0, this function is approaching infinity. And since infinity is not a number, we can also say that this limit does not exist. However, we're going to see in the next examples that there are some functions where the limit does not exist and it's not equal to plus infinity or minus infinity. So oftentimes, you should specify it doesn't exist, but it is at infinity, and then only writing that it doesn't exist when it doesn't exist and is not plus infinity or minus infinity. So let's see an example of one of those limits. Let's define a new function, f of x equals x plus 1 if x greater than or equal to 0, and negative x minus 1 if x less than 0. So if we were to graph this function, we see that for values up to but not including 0, the function can be represented as a downwards line like this. And then for positive values including 0, the function can be represented as an upwards line like this. So let's now try to compute the limit of f of x as x approaches 0. And we're going to run into an issue, which is that as x approaches 0 but is greater than 0, the value that f of x is approaching is 1. But as x gets close to 0 but stays smaller than 0, the value that the function is approaching is negative 1. So it seems that the function is approaching negative 1 and 1 at the same time. We can't represent that as a single number. So we say that this limit does not exist. However, notice that if we're just looking at approaching 0 from the right or just approaching it from the left, then both of these two limits do exist. So this brings us to a new definition of side limits. So we can write a side limit like this: limit f of x, x approaches 0 plus. So what this is saying is, as you take x values that are getting closer and closer to 0 but stay above 0, what is the value of the function approaching? And in this example right here, we see that this function is approaching 1. Then we can also define the limit of f of x as x approaches 0 minus. So this is asking, as we approach 0 but stay below 0, what are the values of f of x approaching? And the answer in this example is minus 1. So for this function, we see that both the limit as you approach x from the left and x from the right both exist. However, they are different numbers. And when we're talking about the limit as x approaches 0 and we don't specify, we mean as x approaches 0 from both directions. And since this function is approaching two different numbers, depending on which direction you're approaching from, we say that this limit does not exist. Now let's see one more example of a function where both the overall limit and both of the two side limits don't exist. So let's consider the function f of x equals sine of 1 over x. So basically the way that this function works is for really, really big values, this function changes really slowly. So if we were to evaluate this function at 100, it would be sine of 1 over 100, or sine of 0.01. And then if we sub in x equals 101, we instead have sine of 1 over 101, but this is equal to sine of 0.0990 approximately. So we see that despite changing the value of x by one whole number, the value of the function barely changed at all. But if we instead take really small values for x, so let's evaluate this function at x equals 1 over 4. So this will be sine of 1 over 1 over 4, or sine of 4, which is approximately 0.25. And then let's evaluate the function at a different point, really close to 1 over 4, like 1 over 5. So this will be sine of 1 over 1 over 5. So sine of 5, which is approximately. So in this case, changing our values of x by only a little bit had a much more noticeable effect on the value of the function. So after seeing this, the graph for the function will be a bit less surprising. What this function looks like is a sine curve, where for big numbers, the sine graph oscillates really, really slowly, but then as you approach 0, the oscillations start to speed up very rapidly. And as you approach 0, it starts to oscillate infinitely fast. And then the same happens on the other side, where it starts oscillating infinitely fast, and then it quickly slows down as you get away from 0. So if we were to compute the limit of this function at 0, we can see that it's not going to exist, because as you take x values that are getting closer and closer to 0, f of x is not converging to one specific number. It keeps switching between anywhere from 1 to -1 and any of these numbers in between. And as you get closer and closer, it starts changing faster and faster and faster. So as you approach 0, f of x still takes all values in this entire range. We can't pinpoint a single number that it's converging to. So we see that this limit does not exist. And also notice that the limit of this function from both, as you approach 0 from both the right and the left, these also do not exist for the same reason.